Hello, fans of using a children's program to do advanced structural mechanics. We will build on the previous lesson, which was just an introduction to using equations, but now we're going to take it a step or two higher up, and we will solve this problem from Professor Bodinas' book. It's problem 1.9, and there's something really nice about the problem, and it allows us to explore some of the computational power of this children's program, GeoGebra. And most importantly is this equation right here. The stress equation is given to us, but the question is, what is the net force in the x direction? X is typically along the axis of the member. And what is the net moment about the z-axis? So that's your typical bending moment. Your thumb is coming out of the page. What is atypical, however, is that I want you to do this in an integral format. I want you to express the force as an integral and the bending moment as an integral using this stress function. So I'm sure almost nobody has done this before in the undergraduate curriculum. And there's another beautiful little subtlety here, and I wrote it down here. Notice that the neutral axis is not at the center of the beam. Once again, you're typically used to seeing the neutral axis as a geometric quantity, but ladies and gentlemen, it isn't. Neutral means that the axial stress is zero. So how could this be possible? And the answer, I think, is hopefully obvious after a bit of reflection, that there is an axial load on the beam as well as a bending moment, because I just asked you to find the axial load and the bending moment. So the stress distribution is not induced solely by bending moment, and that is a thing of beauty. There's so many beautiful things here. It's just, I'm getting teary-eyed. The only thing that I don't really expect an international audience to appreciate or understand even is this ridiculous imperial units that we use in the United States, inches. But I'm not going to use any units other than inches and pounds. And if you want to imagine those as metric units, that's fine for my international friends here. Okay, so how do we do this? So we'll start off a new file here. And as always, I like to make the font bigger. You don't have to do that, but for a video it makes sense. And this one you should do. Turn off the new labeling on objects. The next thing is I would like you to put in some of the terms that we were given. So we were given the width of the beam and the height of the beam. The width is in and out of the page. He calls it depth, which I don't like. So I'm going to call it B for width, as in BH cubed over 12, and it's just 1 inch. The height is 3 units of length. We'll need the moment of inertia, of course. BH cubed over 12. We'll need this cross-sectional area. And that's a good start for us, I think. Now, I explained how the neutral axis is not at the center of the beam. Where is it zero? Where is it zero? And that is not given in this picture, problem 1.9 in Bodinas' book. But we do have a distribution here. Sigma x is given as 2,000 times y. Y is the vertical geometric entity of the cross section, plus 500. And psi for my international friends means pounds per square inch. But again, you don't really need that. So what we want to do is zero out this equation. We will find the zeros of that equation to establish where the neutral axis is. To do that, we have to open up the editor called CAS. This is called Computer Algebra System. And now we have a new window, and it is fairly intuitive, I think. It kind of makes sense, sort of like a MATLAB version of what you would have done. So it's solve, I think it was 2000y, right? Yeah, 2000y, 2000 times y, and a multiplication is a space bar, or you could put a star in, plus 500 equals 0 for y. And the answer is -1/4. So that means the neutral axis is down 1/4, and here it is drawn to scale. Ladies and gentlemen, I would like to put that number in here in the algebra window now. So I'm going to say neutral axis is -0.25. I just noticed that the inertia is given as a symbolic entity. If you don't like that, and I typically don't, you could touch it, right-click, Object Properties, and you get the algebra window, and just turn off the symbolic and close the properties. Now I have that. So now I need to establish how far is it to the tippy top of the beam, and that will be h over 2 plus this little distance, but I made that distance negative, remember? So I will call it y to the max, y max top, let's say, is equal to h over 2, and I'm going to do minus NA because NA is negative. So if that hurts your head, you could do it another way. It's clearly 1.75. And the other one is clearly 1.25, but don't type in 1.25. That would be terrible because you want this to be a parametric script. Y max to the bottom. Y max to the, and I like to capitalize this. Do you notice how I'm doing that? So it separates the letters. GeoGebra is case sensitive, so be aware of that. You must use the letters properly. Y max bottom is h over 2, and that will just be plus NA here, and that gives me the 1.25. Okay, so now how do I get the force? Because your typical undergraduate expression would be sigma is minus mz times y divided by the moment of inertia plus or minus the axial force divided by the cross-sectional area. But I don't have the moment, and I don't have the force, and I have this stress distribution. And this is nice, I think. I really like this, because what we have to do is we have to integrate the stress from the top to the bottom, and that's not going to give me a force yet. I need to multiply that by a width. So ladies and gentlemen, a stress, as you know, is a force, is a stress times an area. So the force is the stress times the area. Now here the width is constant, so I simply put that in the integrand, and I can integrate the stress, multiply that by the width. My limits are the upper and lower dimensions of the beam, and I should get the force here. So let's check that out here as and let's have the robot do the integral here. So the integral of, and now what am I integrating? So there's my integrand. It's going to be b. I'm going to put parentheses in here just to be super careful. B times 2000 times y plus 500 going from minus h over 2 to h over 2. Notice it's blue here, ladies and gentlemen, which means that the robot knows what you're talking about. I think that's right. Hope that's right. Yes, it is right. Okay, 1500. Now, what is the moment? The moment is the force times an arm. You know that. So the moment here is y, which is the vertical distance from the F, and we pretend that the F is axially applied on the member here, right? So y times sigma x b dy would give us the moment independent of what I just did. So here you could see in the integrand, I'm actually getting the force times an arm. There's my limits. So let's put that in. So it will be, maybe I should leave this open so I don't screw this up here. Let's put this in here as integral of, oh, and there's a minus sign here, right? Integral of, it's minus y times the quantity 2000 y plus 500 times b. Hope all that's right. I'm going to surround this by parentheses. That is my integrand. Looks okay, I guess. Minus h over 2. Oops. Minus h over 2 to h over 2. Close that. Hopefully, yes. Okay, we get minus 4,500 inch-pounds. So that is kind of astonishing. What I'm going to do now, ladies and gentlemen, is put that over in the algebra window just so I have it in my pocket when I'm comparing to the undergrad version, F. I just call it F, or I'll call it force. Force is 1500, and mz is minus 4,500. Again, the units are buried in there. I'm using inches and pounds, but if you want to do something else, you can. Now, here's my reality check. My reality check. What is the undergraduate expression? So here it is. The undergraduate is mzy over I with a minus sign plus f over a. So let's program that in here. And we could close our CAS window now. We just did it to get those moments, right? So my undergraduate expression for stress is sigma top, I guess let's call it, via undergrad is mz over I minus mz times y to the top, max top, over inertia plus the force over the C sectional area. And there's the 4,000. That's pounds per square inch. And I will compare it to the equation. I will compare it to the equation. And then you could do it for the bottom also. I'll just stop the video after this. Let's compare it to this equation that Professor Budinas gave us. And I hope your heads explode here. Sigma top via the equation is equal to, this one's super easy, y max top plus 500. And drum roll please, there it is. So we matchy-matched at the top. You could do the same for the bottom, but this was I tried to keep these videos short. This was a tour of CAS. Remember where that is. It's under View CAS. And most importantly, it's a review of this concept of integrating to get entities in engineering mechanics.